Thank you. 皆さんこんにちは。My name is Jon Reid, and I work as an iOS developer at American Express. Today, I want to talk about mock objects, how to make them in Swift, and how to make them more powerful and flexible. But first, why do we need mock objects? Why would you ever want to use a mock object instead of the real object? Let's think about a restaurant where we order a meal from the waiter, and the waiter gives our order to the cook. In a unit test, we don't want to use the real cook. Why not? The real cook takes too long. Or the real cook is not always there. And real cooking uses up resources, so it affects global state. For unit tests, we want to use a fake cook. Instead of testing the results of real cooking, we instead test how the waiter communicates with the cook. This is an interaction test. The tests define a contract of messages the waiter sends to the cook. In Swift, we can usually substitute a fake object for a real object by defining a protocol. We use that protocol in our production code. And then we can substitute anything that satisfies that protocol, whether it's the real object or a fake object. So let's talk more about cooking. Let's say we have a protocol with a method to cook ramen. We can specify the number of bowls we want. We can specify the type of soup from the ramen soup enumeration. We can have extras or toppings. Since cooking takes time, we would normally have a completion handler, but that gets complicated for our example, so let's forget about that for today. Here's code for the waiter. The cook is a constant, which we provide during initialization. The actual waiter code would probably use the builder design pattern to build the order gradually. But for our example, let's just hard code an order method, 2 bowls of miso ramen with wakame and tamago. So, how do we test this method? On the test side, what we do is create a mock cook. Its implementation of the cook ramen method doesn't do any cooking. Instead, its job is to capture information about how it was called. This is the important job of a mock object, to record the messages it receives. In the unit test below, we create the mock cook, we inject it into the waiter through the initializer, then we call the method we want to test, that is, the order method, which will actually call cook ramen. And finally, we have to assert something. In an interaction test, we have a relationship between capturing information on method calls and asserting things about that captured information. Let's start with the most common pattern I see with Swift mocks. Many people assert that the expected method was called like this. To do that, many people add a Boolean property. The mocked method sets that property to true, indicating that the method was called. But there's a problem with this approach. It's throwing away information. The Boolean only tells us that the method was called when it's usually a problem if it's called more than once. So instead, let's record how many times the method was called. Let's change the property from a Boolean to an integer and simply increment the count. This changes the test. Now we can say the OCHramen call count should equal 1. Now, recently, one of my tests caught an error by reporting that a method was called twice instead of once. I had made an error during refactoring, and the test let me know. So this is important, not just for checking our first implementation. It's important for future refactoring. Now that we have the call count, let's capture more information about the method parameters. Let's store each argument in a property. First, the number of bowls. Then, the type of soup. Then, the array of extras or toppings. But again, we're throwing away information. All we're doing is saving the last set of arguments. But usually, it's okay to keep only the last set of arguments. So let's at least be more honest and clear about that. We can name the properties to make it clear that we only have the values from the last call. So now we can have a test like this. We assert that the call count is 1, the number of bowls is 2, the type of soup is miso, and that we have 2 extras, wakame and tamago. And this test works. Yay! There's a rule of thumb that a unit test should have 1 assertion. That it should assert 1 truth. Here we have 4 different assertions. It would be nicer to express this as a single assertion, especially when we have multiple tests. This is pretty easy to do, just by extracting these assertions into a new method in the mock object. The test now calls verify OCHramen. But what does this do to error messages? Let's change the number of expected bowls from 2 to 3, just to make the test fail. The error we will get is that 2 is not equal to 3, and it will point to the failed assertion. It's pointing to the helper method, not to the test. This is a problem, especially with multiple tests calling the same helper method. We can fix this by adding 2 parameters to the helper method. All we have to do is capture the file name and line number as parameters with default values. Then we pass those parameters to the assert statements. Now, when we get a test failure, it points to the verify statement that failed in the test. But this isn't a very good error message. It just tells us 2 is not equal to 3. 2 what? 3 what? Let's specify the what by adding a message to identify each assertion. Call count, bowls, etc. Now, the assertion failure says 2 is not equal to 3 bowls. This is a useful error message. Now, what about this array of extra toppings? What happens if we reverse the toppings? We want this test to still pass because we don't care about the order of the array. We only care about the contents of the array. When we run this test, we get this error message. This is an example of a fragile test. It breaks even when we don't want it to break. A fragile test is oversensitive. It may pass today, but tomorrow it may break due to a benign change in the production code. We don't want to discourage changes to code. Ideally, with unit tests as our safety net, we're encouraged to change our code. We want tests to give us confidence so that we can make bold changes. Then we can practice continual refactoring, which is necessary because the forces on our code keep evolving. We can only be as agile as our code lets us be. So we want tests that confirm correctness, but not tests that keep us from changing the code. We want tests that are sensitive to things that are important, but ignore things that are unimportant. So let's make this test less fragile. Instead of specifying an array of extras to match using equality, let's specify a predicate. That is, we specify a closure that takes the argument and it evaluates to true or false. So here we can say we want the extras array to have 2 items, that it should contain wakame, and that it should also contain tamago. This test passes regardless of the order of the array. It checks what is important, but ignores what is unimportant, and that makes it easier to refactor our production code. Here's how we change the verify method to support this. We change the parameter that used to accept an array of strings. Now it takes a closure that evaluates an array of strings, returning a Boolean. In the assertion, we pass the captured extras to the predicate and assert that the result is true. Finally, where xct assert equal reports both the expected value and the actual value, xct assert true does not. So, in the failure message, let's report the actual value. Our test with the correct extras in a different order now passes. And if the test fails, say we get nori instead of wakame, the error message is pretty good. It's pretty good, but it's not great. It's okay in our IDE when the data is small. But if the data is large, it gets harder to visually find the mismatch. And what if we're not in Xcode or app code when we read the error? What if it's in the output of our continuous integration logs? Then we'll see the actual value, but we don't know what the expectation was. Wouldn't it be nice to have a predicate with more detailed output? That's exactly what OCHamcrest matchers are. Matchers were originally invented as part of JMock, the very first mock object library. They were then extracted to their own library and even became part of JUnit. OCHamcrest is implemented in various languages, including Objective-C and Swift. OCHamcrest matchers do a number of things. A matcher is a predicate that evaluates a value. A matcher describes itself. That is, it describes its expectations. If there is a mismatch, a matcher can give precise description of what's different from the expectation. They can be composed from other matchers in a domain-specific language. Nested matchers, that is, matchers made from other matchers, are especially powerful for evaluating collections. And OCHamcrest is not only a library of predefined matchers, it's also a framework for writing your own custom matchers. To make it easier to use Swift OCHamcrest matchers in mock objects, let's make a helper. The switch statement calls matches. If the result is a match, there's nothing to do. If the result is a mismatch, we get the mismatch description as an associated value. Then we call xctFail, adding a label to identify what we're checking. This is how we call it in our verify statement. First, you see the argument type is a matcher of an array of strings. And then we call our new helper with the label extras. Remember, this is what our test code looked like when we just used a closure. This is what it looks like when we add OCHamcrest support. Contains in any order is a predefined OCHamcrest matcher. Let's change the extras from wakame to chashu, sliced pork, just to make the test fail. Here's what the failure message looks like. If you read the end, which is the second line, it describes the expectation. Expected a sequence containing in any order with tamago and chashu. Now read the beginning. It tells you the actual value of the extras parameter. Then it tells you in detail about the mismatch. Got wakame, expected chashu. Now we have a test that isn't fragile, which also gives a very detailed error message. When a unit test failure gives us enough information, we can often figure out what's wrong just from the test name and the failure message. So what happens if we use matchers for each parameter in our verify method? This is very similar to the first time we created this helper method, but now we're no longer calling xct assert equal. Even for the call count, which has an implicit expectation of 1, I'm using an equal to matcher. In the test code, we can still test for equality where we want to by using the equal to matcher. but the mock object is no longer restricted to equality. For example, for bowls, we can say greater than or equal to 2, if that would make our test less fragile. Or maybe this test shouldn't care about the type of soup, so we use the anything matcher. And look at the last matcher for our extras. We don't have to specify 2 strings. We can specify 2 matchers instead. When they're both equal to matchers, that's the same as what we get with 2 strings. But we can use other types of string matchers. For example, has prefix to check for a string prefix. Going back to the beginning, when should we use fake objects? Use fake objects when the real object is expensive. Maybe the real object is too slow. Maybe it's unreliable. Or maybe it changes global state. These are all good times to use a fake object. And a mock object is a fake which you can ask, were you called the way I expected? Here are my recommendations for creating more powerful mock objects in Swift. First, don't use a Boolean to record whether a method was called. Instead, use an integer to capture the call count. When you see multiple asserts against a mock, try extracting a helper method. Add file name and line number to that helper method and pass those to the asserts. Add messages to each assert so we can tell them apart. When necessary, don't assert using equality. Instead, use predicates so that the test code can be more flexible and less fragile. Finally, consider using OCHamcrest matchers, which are like predicates on steroids. Remember, our goal isn't just to have tests. It's to have tests that enable and encourage refactoring. So we want tests that are sensitive to things that are important, but ignore things that are unimportant. We don't want tests that break like glass. Instead, we want tests that are like bamboo, strong, but flexible. If you want to see sample code or get a copy of these slides, please go to my website. Thank you.